One special application of hydrogen bonding is about methane hydrates, sometimes called methane clathrates, and also other names. And in this situation, where you have to have very, very cold temperatures, the crystal structure of the ice contains an opening, a cavity, if you will, on the inside that is just big enough that small molecules can be trapped inside. In particular, a very small molecule such as methane. And what this means is that if you were to dig up some ice which has methane because of pressure and cold temperature trapped inside the cavities or the openings inside the crystalline structure, you could actually light that ice on fire and it would burn. Imagine an ice cube, for example, that is on fire. We have vast deposits of these hydrates underneath the ocean, and especially in the Arctic region, because of course you need an awful lot of cold and you need the pressure that pushes this methane and traps this methane inside the crystalline structure of the ice. It mentions here, for example, 10 to the 13 tons of carbon are perhaps present in these hydrates, these methane hydrates, and that's about the same amount as the reserves of coal, oil, and natural gas. That's an awful lot of energy. It's an awful lot of a resource material that we might be able to harness if we can figure out the technology. Interestingly enough, your text doesn't mention it here, but we also suspect that there are methane hydrates farther out in space on maybe some of the planets that are farther away from the sun than we are. Maybe perhaps even on the moon. But the point being that if there were methane hydrates and we were to travel there, not only would we have a source of methane, which would be an energy source to generate electricity, for example, or to generate heat, but you would also have water as a product of that as well. And of course, you would need water. What are the downsides of methane hydrates, or one of the challenges? First of all, one significant problem is how are you going to get this from deep under the ocean? And that's going to be a challenge. This would be in the crust underneath the ocean, especially in the polar regions. That's a technology problem. The other problem is that there's a tremendous, methane is a greenhouse gas, and so you would want to be able to access this methane without it escaping into the atmosphere and be a greenhouse gas. We should also mention that this is a suspect, this methane hydrate being released from the Gulf of Mexico. You might remember the Deepwater Horizon rig where it was on fire for a number of months, actually, because of the methane that was escaping from deep under the Gulf of Mexico. And there's even a movie about this as well. Over here, they mention that on the North Shore, 2,400 billion cubic meters of methane, which is the equivalent of 4 years of United States natural gas production. So that would be an awful lot of resource material should we ever access that. Well, let's go ahead and finish the chapter and focus our attention on intermolecular forces involving nonpolar molecules. In the previous section, you learned about ion-ion, what would be a previous chapter, or ion-dipole interactions, and dipole-dipole interactions, and the most important kind of dipole-dipole interaction, which would be hydrogen bonding. But what about dipole versus induced dipole forces? And so here you're going to need one molecule that is polar, and you're going to need another molecule that is nonpolar, but because of the distribution of electrons around that nonpolar molecule, that distribution can sometimes become unbalanced, and so it can be temporarily polar. Or that polarity can be induced, even though the molecule itself is nonpolar, should something make that distribution of electrons become unbalanced. So one side is a little bit more negative than the other. It might be a collision with the sides of the container. It might be a collision with other molecules. Or it could be a collision with a polar molecule that could induce the polarity. For example, you can take a balloon, rub it on your clothing or hair, and it can become polar. Then if you take that polar balloon and bring it up towards a wall, a dry wall, you can induce a polar region in the dry wall when the negatively charged balloon gets close enough to the dry wall and cause the electrons in that region of the dry wall to be repelled, creating a temporarily positive region in the dry wall, and now the balloon will stick to the wall. That would be maybe an example of a dipole, the balloon, and an induced dipole, that region of the wall interaction. So you can have dipole, induced dipole interactions. One is going to be a permanent dipole because of the geometry or structure of the molecule, and the other is going to be an induced dipole. That would be a nonpolar molecule, but the bigger the nonpolar molecule, the more electrons there are, and the more likely you're going to have more electrons on one side of the molecule than the other, creating a temporarily induced dipole. Now, the process of inducing a dipole is called polarization, and you come across this word in a lot of different contexts in chemistry and physics. For example, you can put molecules inside a region that is electrically charged. If I had two metal plates and I connect them, for example, by a wire to a battery, so let's say this is a battery and there's the positive end of the battery and there's a negative end, and I connect it like that. In this space between these two metal plates, let's say they're copper, once the battery is connected, you can create an electrical field so that any material, and it just erased on me again, so that any material that is in between these two metal plates can have all of their molecules that make up that material become polarized as they align themselves between the negative and the positive metal plates. That would be polarizing that material. In physics, you'll learn we call that material a dielectric. And so a lot depends upon the polarizability of the atom or the molecule. And if you think about it, the bigger the atom, in terms of the number of protons and electrons, or the bigger the molecule, the more easily it can be polarizable by getting an imbalance, an uneven distribution of the electrons around it through all kinds of different means, such as the description that I made over here, or such as by bringing it into the proximity of a polar molecule. And we can use this to help us to understand some of the trends that we see when we look at various materials. For example, in table 12.3, you'll notice when we think about solubility, if we talk about hydrogen to oxygen, you can see the molar mass gets bigger and bigger, and the solubility also becomes bigger and bigger. Because in order to be soluble in water, water is polar, so like dissolves like, and if you have some large molecules compared to small molecules that are more easily polarizable and can more readily have an imbalance in electron distribution because you have more electrons, you can see that your solubility gets greater and greater because the polarness, so to speak, of that molecule becomes greater and greater. Also, when we look at table 12.4, you can see again that if we think about the heat of vaporization, the enthalpy of vaporization gets greater and greater as your molar masses get greater and greater. Of course, we're talking about 14 and For nitrogen, 14 and 14 gives me 28 for nitrogen, and oxygen, 16 and 16 gives me 32. But as we go down this list here, my molar masses get bigger, and as a result, the number of electrons that can be unevenly distributed gets bigger and bigger. In other words, the greater the polarizability of the molecule becomes, which means my induced dipole attractions are going to get stronger and stronger. And therefore, we expect the boiling point to get greater and greater, because it's going to take more and more energy to separate the molecules that have a high induced dipole compared to the molecules that have a weak induced dipole. And if you remember anything in biology, you might remember that many organic and bioorganic molecules involve hydrogen bonding, particularly in DNA. So we have a bond there and a hydrogen bond there. These hydrogen bonds between adenine and thymine, or guanine and cytosine, are the result of these interactions are the result of hydrogen bondings, and that makes the DNA molecule a relatively stable molecule, because these base pairs are held together pretty strongly. Not that you can't overwhelm them through heat or some other means and break them apart. Obviously, for DNA to replicate itself, it has to be completely unraveled, and in order for one strand of DNA to become two DNA strands during the cell cycle division. Remember IPMAT, interphase, prophase, metaphase, anaphase, telophase. The DNA makes a copy of itself. So you can't have an energy involved in these bonds that is so great that the DNA molecule can't unravel and become replicated. Over here again, you can see the hydrogen bonds all the way through. You might remember some of the history, including Rosalind Franklin, who did all the background work and often gets none of the credit. She unfortunately died at a rather young age, and in all likelihood should have received a Nobel Prize for her work. Here's an example of induced dipole interactions. We begin with two particles, in this case, could be atoms, could be molecules, that are nonpolar, but if they get close enough, or if there just happens to be, through sheer statistical probability, an imbalance so that more electrons are located on one side compared to the other side, we now have a momentary dipole, which can create a momentary dipole in another molecule, and the opposites can attract. And as a result, two particles that might be in the gaseous state could actually become in the liquid state. And of course, even nonpolar molecules can be in the liquid or solid state, which means there's got to be some type of force of attraction between the particles at those low temperatures. And in general, we call those the London forces. Now, coming over here, we mentioned the fact that a dipole can be temporarily induced, meaning the molecule does not naturally have a dipole, but through sheer chance, you can get more electrons on one side than the other, in which case it temporarily becomes a dipole. That's when it gets induced. And then, of course, as a result of that, you can have your intramolecular attractions. You can now have your van der Waals forces. In this case, the particular van der Waals forces, again, are induced dipole. Sometimes they're called dispersion interaction forces. Sometimes they're called London forces. And you can see here that even iodine, which is a big molecule, can be easily polarized and have a temporary imbalance with more electrons on one side of the molecule than the other. So it can dissolve in water a little bit. You can tell by the reddish color in the water. Below it, you've got a denser carbon tetrachloride. Now, if you shake up the tube and bring this iodine that's up here in contact with something that's nonpolar, it preferentially dissolves in the nonpolar because, of course, like dissolves in like. And it prefers to be dissolved in the nonpolar carbon tetrachloride. So if we're going to summarize all of this, in an earlier chapter we talked about ion-ion in ionic bonding in ionic solids and ionic crystals. But now we're talking about particularly molecules that naturally have a dipole, or dipole-dipole interactions, the most important of which is hydrogen bonding, which is stronger than dipole-dipole. So that's why it's listed there. So go at the top is 1 because of the ions, number 2 because of hydrogen bonding, number 3 because of natural dipoles, number 4 because of a natural dipole and an induced dipole, and number 5, the weakest, because of induced dipole. However, we do need to point out that these can be quite strong when you have molecules that are very, very large. So to summarize all of this, and this is, by the way, what I just said is right there, we have different types of intermolecular forces. Even induced dipole can be substantial if the molecule is big enough. And so when we look here, you're going to notice that in blue is the total strength of the intermolecular force, the total amount of energy it's going to take to separate the two molecules from each other. That's going to be the total. Now, when we start with argon, you'll notice that we don't have any dipole-dipole forces because we don't have any naturally occurring dipoles. But we do have some induced dipole, and that's it, just induced dipole. So the total is just the induced dipole. They're the same. Same with carbon monoxide. If you think of carbon monoxide, and if you were to do your VSEPR thing, it's going to look like this, because carbon is going to have 4 electrons, and oxygen is going to have 6 electrons. That gives me 10 electrons. Therefore, I need 5 pairs. So I'm going to have 3 pairs that are shared, 1 pair there, 1 pair there. And you can see this is a nonpolar molecule. You got a lone pair of electrons there and a lone pair of electrons on the other side. So for carbon monoxide, all you have are induced dipole. Now when we come to hydrogen iodide, there's a little bit of polarity there. So you have just a smidge of this induced dipole. And so you can see your total is just a little bit more than the induced dipole. Then when we come to hydrogen bromide, it's a little bit more distinct. When you come to hydrochloric acid, your dipole becomes even more substantial. And then when we come to ammonia, we have hydrogen bonding. And so my dipoles are even a greater contributing factor, thinking of the hydrogen bonding. And then when we come over here, of course, to water, over here, water, you've got your most substantial hydrogen bonding of all, dipole-dipole interaction. Again, you still have a little bit of induced dipole. And of course, notice that every one of them has, and I'm going to switch colors here, every one of them is going to have induced dipole, because every one of them, there, you have electrons, and you can have an imbalance in the number of electrons. And that's going to conclude our discussion, and that also concludes the chapter.